in one sense, the topic for today, matchings, is both a graph theory topic and a discrete topic. It's a topic about functions. So, I'm going to give away some books. If nobody cares which book they get, I can give out a book to everybody, yes? What if people do care? What if there's a restriction on which books each of you can get? Well, let's create some sort of bipartite graph. I could list all the students, and I could list all the books, and we could create a bipartite matching, a bipartite that says student one can get, I don't know, let's say student one can get book 2, book 3, book 5, right? And I could go through and I could assign a set of edges so that student I gets book J means we create the edge. And now I can ask a different question. Can I give a book to everybody? I'm going to have to know the set of edges for every student, right? Once I have a list of all the edges in this graph, I can ask, is there an edge associated to each student uniquely? Now we see how we talk about this as being a function idea. Is there a one-to-one function from the set of students into, not onto, but into the set of books? Where S is the set of students and B is the set of books, is there a one-to-one from S to B that obeys all of the restrictions? Can we find this? What would be some obvious places where this would fail? Then I'm in deep trouble, right? Now, clearly, in my example with 10 students and 12 books, that's not the case. So how could this example fail? One of the books is a hardback first edition signed copy of Twilight. You could either burn it or sell it for $1 million. I bet everybody wants that book, right? Get rich. I'm never going to read it, but I'll sell it to somebody. If maybe student I gets book J, remember that's a preference or a restriction, right? What if two students each only want one particular book? Aha! So we have to look at the way the edges of this graph, the restrictions on students and books behave. Suppose I can do this. I can get everybody their own book. What would the subgraph of G, our bipartite graph, look like? Go back up here to the picture. I've got all the students at the top. I've got all the books at the bottom. I am able, within our restrictions, to give everyone a book. So let's just look at those edges. What does that look like? There's only one edge between a student and a book, right? And none of those edges are connected to each other at all. I have mutually disjoint, not just internally disjoint, because each path is of only length 1, right? Say student 1 gets book 5. That's the only edge connecting student 1 to anything. That's the only edge connecting book 5 to anything. So if none of my edges are adjacent, then I have what we're going to call a set of independent edges. Same idea. You'll notice there's an adjective missing for those of you in the other class. They're not linearly independent. There's no linear here, it's just independent. So in each case, if we had a way of assigning everyone a book, there were 10 students and 12 books, there would be 10 edges in our set. And none of them would be adjacent to one another. I'd have 10 independent edges. We're going to call a set of independent edges a matching. So now my goal is to find out, do I have particular matchings? Let's start with a bipartite graph. That means I've got partite sets in the vertices U and W, and I'm going to pick the smaller set to be U. And we might as well give a number for the size of the smaller set. So I'm going to let this one, cardinality of U, we'll call that little r. And so in this environment, a matching is a set of edges where the edges go from the U set to the W set. And each of the UI is distinct in capital U, and each of the WI is distinct in capital W. So we never use the same vertex twice in any of our edges. If I want to be able to assign everybody a book, then I need a matching of size R. You use the word cardinality. The size is always about graphs. I'm talking about a set at the moment. Set should have cardinality R. ACDGHPT. I'm a math person, so of course in the example these are all math books. Algebra, calculus, differential equations, geometry, history of math, programming, or topology. Thus the letters that we picked. Now, my 6 students have different interests. And they tell me, oh, A wants D, H, T. That's their preference. B wants G and P and T. C wants A and G and H. D wants H and P and T. E wants A, C, D. F wants C, D, P. Create for me a bipartite graph showing this set of preferences. I did not write down the entire bipartite graph. But are those acceptable edges? Can I give person A the book T? In their want list. Person B, the book G, it's in their want list. Book A can go to person C. Book P can go to person D. E gets book D, and F gets book C. Nobody gets the history book. But everybody got a book, didn't they? I could do it. The actual completed, I don't want to use the word complete because it technically isn't a complete graph, but the full bipartite graph and this matching are here at the top, page 185. Those edges are the ones I drew. How the hell do I find them in here? So right now, it worked. That's the critical question. Oh boy, did you get lucky? How did this work? Let's look at one that fails. I have 7 students looking for jobs. The students are B, D, F, J, K, and L, and M. Ben, Don, Felix, June, Kim, Lyle, and Maria. I have a bunch of jobs available. Counting, consulting, editing, programming, reporting, secretary, teacher. 7 jobs, 7 students. I'm not even going to look at drawing the graph at this point. What I am going to notice is that there are a couple of students with some very restrictive choices here, aren't there? What do you notice about those 4 students? Yeah, they're all after the E job, the editing position. But more than that, look at all the jobs they're looking at together. They all contain E. E, C, and R. 3 jobs being competed for by 4 people. Okay, wait a second. What did I say earlier about when would this fail? This would fail if my restrictions are too strict. If 2 people wanted one and only one book. Well, here I've got 4 people and they're trying to get from 3 jobs. Oh, crap. There's no way to satisfy all 4 students' restrictions. So let me go back to the general idea. I have a bipartite graph. The partite sets are U and W. Let's pick a non-empty subset of U. Call it X. So X is some collection of vertices in the smaller of the 2 sets. I've used this term before, neighborhood. But when I used it before, way back in chapter 1, I talked about the neighborhood of a vertex. Now I'm talking about the neighborhood of a collection of vertices. What's the neighborhood of X? What was the neighborhood of a single vertex? All adjacent vertices. So what I'm going to do is I'm going to take the union of all of those vertices for every vertex in X. In other words, I just don't want the things adjacent to one of them. I want the things adjacent to any of them. Appear to have written this one dry this week. Yep. Paul's condition. After Philip Hall says, I want the neighborhood of a set of vertices to contain more things than the vertices themselves. Now, when Philip Hall actually wrote this out, he wasn't actually doing graph theory. He was doing set theory, looking at functions. So he did this entirely from a discrete perspective. But somebody said, ooh, this is exactly the thing we need to look at our matchings. This turns out to be exactly what I want. What always happens in an if and only if proof? I got to do two of them. But what almost always happens? One of them is a piece of cake, the other one sucks bricks. Yep. One direction is really easy, but it's proved indirectly. What does that mean? If I tell you that Hall's condition fails, at least once, right? Because this is a universal, so its negation is an existential. Then there exists S, a subset of U, the smaller one, S not equal to the empty set, so that NS in size, in cardinality, is less than S. What do you know about N of S, the neighborhood itself? Where do those vertices live? Part of my graph, but there is part of a specific piece of my graph. They're all in W. I can go you a step further. I know that that is strictly smaller than, not equal to. Why do I know it's not equal to? Got to be a proper subset. Promise there's a reason. Visible to you on the screen right at the moment. I'm not making you look for that's way out there. There's less vertices in S than there are in U. There's less vertices in U than there are in W. That's a strict inequality. There you go. And that means that S cannot be matched properly to a subset of W. No Hall's theorem, no matching. Contrapositive. Check mark. That's the short one. The other direction is not. What I need to do is I need to build Hall's condition from the matching. Because I want to go the other way, right? So I'm going to start with Hall's condition and show, hey, I've got a matching. I can do that directly, or I can do it indirectly. If I don't have a matching, I can't have Hall's condition. In order to do this properly, I have to do an induction proof. I'm starting from Hall's condition. I want to end with a matching. What's Hall's condition say? So I start with a non-empty subset of vertices, and I say, oh, the neighborhood of this set of vertices must have more than that many vertices, right? Well, more than or equal to. Wait a minute. All I have to do is match U to W, right? But U only has one thing in it. This has at least one thing in it. Pick one. Matching W. I know that U itself is just one thing. I know the neighborhood is at least one thing. I have a matching. U1 to W1. Check mark. But that's our base case. Oh boy. Doing an induction argument, I need an induction hypothesis. And what's more, I'm doing a strong induction argument. So my induction argument is for all less than, not just for one to the next, but for all of them less to the next. Suppose for k bigger than or equal to 2, if G1 is any bipartite graph with partite sets U1 and W1, size of U1 less than or equal to size of W1, and 1 less than or equal to the size of U1 less than or equal to K. There's the strong part of the induction hypothesis that satisfies Hall's criteria, Hall's condition, sorry. if, then U1 can be matched to some subset of W1. Phew. That's my induction hypothesis. That's just the hypothesis? Yes. It's basically, I'm saying I can do it up to K. So what's the thing I want to show? This is a general question about induction arguments. What's the thing I want to be able to show? I can do the next one. I'm going to make my life slightly easier. Hang on a second. Let's make this strictly less than. Then instead of trying to show K plus 1, I'll be trying to show K. I want to show that I can do this if the size of this set U1 is actually equal to the next number. So I'll start with the same assumptions. I have a bipartite graph. It's got partite sets U and W. The size of U is smaller than the size of W. And Hall's condition is satisfied. A lot of setup here. So notice this time, I actually want to say, oh, the set U is size K. I want to show I can do this. I can do what? What's the thing I want to be able to do with that set U? The this I want to show is that I can match U to some subset of W. What's Hall's condition? I've asked this now 3 times. You should be able to say this fairly quickly. What is Hall's condition? Okay. Greater than or equal to, right? 2 choices, greater than or equal. Case 1. For every subset of U that is not all of U, let's suppose it was strictly greater than. Because it said greater than or equal to, right? So I'm going to assume all the time it's greater than. Oh, okay. Then let me pick one of the vertices. That's a subset of size 1, right? By definition, by our case here, the neighborhood of that vertex is at least 2. So let's take one of those in the neighborhood. And let's take away those 2 vertices from G. Tell me why I can now do something that's induction. I'm now using size k minus 1. By our induction hypothesis, I know that U minus U and W minus W have a matching. If I add the edge UW, I have a matching in U. It worked. I made it smaller using induction hypothesis. Oh, then just add this one edge back in. Poof. That's case 1. That's the end of class. What are we doing on Monday? Case 2. And more stuff. I will see you all then.